For decades, industrial predictive maintenance suffered from a logistical flaw known as the identification error. A technician could easily point an analog infrared sensor at a failing component and record a critical temperature spike. But in dense, high-stress environments featuring hundreds of identical repeating assets, reliably matching a raw data point on a clipboard to the specific physical valve or breaker days later was highly prone to failure. To address this gap between raw measurement and contextual proof, engineers developed the Raytek PhotoTemp MX6. By integrating a digital camera directly into a precision infrared pyrometer, it established a simultaneous workflow: measure the temperature, photograph the specific target area, and document the resulting data as a single combined digital asset. Predictive maintenance requires verified visual databases to function properly. If a technician cannot locate the exact component that triggered a high temperature alarm, the recorded data cannot be accurately translated into an actionable repair order. The engineering of the MX6 reflects the physical realities of industrial auditing. The device utilizes a tactical pistol grip silhouette weighing exactly 480 grams. This specific form factor reduces operator fatigue during hours-long inspection routes while providing the mechanical stability required for high-precision aiming. The operational sequence relies on a dual-action trigger constraint. Pulling the trigger activates the true dimension laser and the internal temperature sensor. Releasing that trigger immediately fires the camera lens, supported by an intelligent light sensitivity flash that automatically deploys if ambient lighting drops below 6 lux. Internally, the hardware executes a strict logging sequence. It locks the precise temperature readout, the time and date metadata, and the captured JPEG into an unalterable digital file, permanently binding the thermal data to its visual context. To make this volume of data actionable, the files are offloaded via USB 1.1 into the proprietary PhotoTemp MX software ecosystem. Here, engineers track long-term thermal trends to monitor mechanical wear over months or years. The software allows managers to preload up to 100 highly specific location names, such as Transformer A South Bushing. As the technician walks the route, the MX6 displays exactly which component to measure next, effectively eliminating the risk of manual data entry errors. By hardwiring the data capture to the photographic evidence and routing it through structured software, the MX6 replaced isolated analog readings with a rigorous, verifiable digital audit trail. That audit trail only works if the initial thermal data is accurate. A non-contact infrared sensor does not measure a single microscopic point. It measures the average temperature across a circular surface area. This diagram demonstrates the distance-to-spot ratio. Spot size equals distance divided by the instrument's D to S rating. The MX6's 60:1 ratio measures a 1-inch target from 60 inches away. If the component is smaller than this spot size, the sensor absorbs background radiation, corrupting the data. Standard off-axis lasers create parallax error, missing the sensor's true center. The MX6 uses a coaxial system projecting down the optical center. Its 635 nanometer laser circle expands and rotates with distance, showing the precise boundary of the averaging zone. If the optical boundary isn't perfectly matched to the physical target, the thermal data will be false. By eliminating parallax error entirely, the coaxial optics ensure the digital photograph captures the exact area the sensor analyzed. At the sensor level, measuring that precise targeted zone requires strict adherence to the laws of thermodynamics, specifically the principles of black-body radiation. All objects above absolute zero emit electromagnetic radiation. To capture this, the MX6 utilizes a specialized thermopile detector calibrated to isolate thermal wavelengths strictly between 8 and 14 micrometers. This electromagnetic spectrum chart highlights the 8 to 14 micrometer atmospheric window. In this long-wave region, water vapor and carbon dioxide don't scatter infrared radiation. This lack of attenuation allows the hardware to calculate extreme temperatures from -30 to 900 degrees Celsius. But real-world objects do not emit thermal energy with perfect mathematical efficiency. This physical deviation is measured as emissivity. Oxidized metals and organic materials have high emissivity, effectively radiating their own internal heat. Shiny, polished metals have incredibly low emissivity. Instead of emitting their own temperature, they act like thermal mirrors, reflecting the infrared energy of the machinery operating around them. To correct for this, the MX6 allows technicians to manually adjust the emissivity baseline in precise 0.01 increments. For completely unknown materials, it includes a physical Type K thermocouple probe to execute a direct contact baseline reading, allowing the user to calibrate the optical sensor perfectly on the spot. This thermodynamic compensation ensures the detector is never fooled by environmental reflections, guaranteeing the captured data reflects the true structural state. Applied in the field, these exact thermodynamic tolerances dictate safety and continuous production across heavy manufacturing. Different environments demand highly specific focal behaviors. For electrical benchwork, engineers utilize the close focus, or CF model. It employs a tighter 50-to-1 distance ratio, allowing a technician to isolate the exact temperature of a microscopic 6mm resistor on a dense circuit board without pulling in ambient heat from adjacent components. Conversely, the Sub-Zero variant was engineered strictly for the logistics of the global cold chain. Its sensors are recalibrated for extreme accuracy in commercial walk-in freezers down to -50°C. In a food safety compliance workflow, an inspector scans a pallet on incoming frozen goods, verifying a strict -20° surface reading, while simultaneously photographing the physical shipping label on the box. Deploying the correct optical variation for the specific environment completely eliminates ambiguity. The data proves the temperature, and the embedded photograph proves the identity. The long-term value of the MX6 lies in how it reorganized the basic philosophy of industrial asset management. By synthesizing applied thermodynamics with phi-ratio coaxial optics and an immutable digital logging sequence, it structurally solved the identification error that had plagued inspection routes for decades. When technicians were forced to rely on isolated, easily conflated analog data, facilities defaulted to a reactive, fail-and-fix maintenance model. Parts were often replaced after they had already caused a shutdown. The MX6 enabled a transition to proactive condition monitoring. Managers could verify exact component degradation over time through photographic databases, allowing them to adopt an identify and schedule approach that replaces parts during planned downtime. By integrating digital imaging with high-ratio optics, the MX6 established the verifiable digital workflow used in modern global